All right, with this module, we're going to start a new chapter and topic on polymers. So, polymers are these large molecules, as you can kind of see here from the diagram. And because of this large size, this long chain for most of them, we refer to them as macromolecules. And so, for this first module, we're going to go over some introduction to polymers, their basic properties, and the way they're structured. And we're going to start with this module by looking at sort of a brainstorm. And so we're going to go to the quiz. And what I want you to do is brainstorm a list of properties that you think are typically associated with polymers. Also, you might refer to them as plastics. So see if you can list some properties, common properties that you think are associated with these materials. So do that, go to the quiz, do that and come back, and then we will discuss some general properties. All right, so let's take a look at some of the general properties that you've listed. And so these are the big ones. You might have listed some that don't appear on this list, and that's okay. But the main ones are that polymers are typically considered lightweight. So you might think of them as canoes or kayak material, right? It's able to make that light so that you can transport it very easily. They, because of the weight, but also the way we can manufacture them and a lot of different techniques, they're very inexpensive to manufacture. They have moderate strength. So metals, ceramics tend to have are much stronger, but polymers can have kind of moderate strength, enough for quite a few applications. Also, quite a few polymers have rather high toughness. So we just talked in the failure chapter about toughness, fracture toughness. So that's the ability to absorb energy before failure. And so things like helmets, bulletproof glass, right? All of those are applications where you want high toughness. On the other hand, they are not suitable for very high temperatures. So they tend to either decompose or melt, or change shape at high temperatures. So that's around 200 Celsius is typically around the upper end. There are some exceptions. Silicon, as you might be aware, is kind of used in a lot of new baking and kitchen applications that has a higher temperature. But for the most part, generally not considered high temperature. For that, you'd want to go to metals or even ceramics for even higher. All right, so let's talk a little bit about how a polymer is put together on the molecular end. And so a polymer is basically a molecular unit that is repeated many times. And so that's actually where the name comes from. So poly means many, and mer refers to a repeat unit. And so basically we have many repeat units. So a very common type of polymer is a chain polymer. And so that's where it has this kind of long chain-like structure. There's also network, but a lot of what we'll talk about is chains. And so for polyethylene, for example, PE, and you might have seen this on recycle codes and so forth, but this is the repeat structure is two carbons bonded together filled out with hydrogens off of that chain, and that is then repeated over and over again many times to give us a macromolecule. We can change what is off of that carbon, what we call the carbon backbone. We can change it from hydrogen to other things. If we change one of them for chlorine, we get polyvinyl chloride, or PVC. If we introduce the CH3 group, we get polypropylene, or PP. All of these are variations of the same vinyl polymer, as we'll talk about later. But the important thing to kind of mention here about the bonding, because in the bonding chapter, we talked about the different types of bonding associated with different classes of materials. Here, the intramolecular bonds, so those within the molecule itself, are covalent. So the carbon-carbon bond is covalent, the carbon-hydrogen bond is covalent, all of those are covalent. However, a lot of the properties are going to be dictated by this chain bonding with the next chain. So, for example, if you put another chain of polyethylene next to polyethylene, there's going to be bonding between the hydrogens. And so that's going to give us van der Waals or secondary bonds. And so that's the intermolecular, so between polymers bonding. So it's important to mention that there are covalent bonds within the macromolecule, but the van der Waals, which are what define a lot of the properties, are those governing between different polymer chains. All right, so then the idea of the repeat unit is within this macromolecule, the repeat, what is repeated, and in this case it's 2 carbons and 4 hydrogens repeated. So this is the repeat entity in this long chain or in a network. A lot of people will use the term repeat unit and monomer as synonyms, but they're actually a little bit different in meaning. The monomer is not the repeat unit, so it's not this structure. The monomer is actually the molecule from which the polymer is synthesized. So polyethylene, which is shown down here, is synthesized from ethylene gas, and that's and you see a very big similarity here, but the difference being that the carbon is doubly bonded so that it's an isolated molecule. It can't form that repeat structure. So in the process of synthesizing, which we'll talk about next, this carbon double bond is broken and it allows us to form a chain. So the monomer is the molecule that makes the polymer. So there's a subtle difference between a monomer and a repeat structure or repeat unit. All right, so when we talk about polymers, it's useful to talk about hydrocarbons because hydrocarbons and chain polymers tend to share a lot of properties, and there's essentially there's a subtle difference between the two. So let's just look at the simplest hydrocarbon we can have, and that's methane or CH4. So we have carbon bonded to 4 hydrogens. It has a very low boiling point, so it's a gas for most intents and purposes. If we keep adding carbons, and we have a carbon-carbon bond, and then the rest are filled out by hydrogens, we have C2H6. This is ethane, and it has a slightly higher boiling point. And then we go to propane, which we're continuing to add carbons. So we have basically a single carbon, a double carbon, and a triple carbon, and you're starting to see the formings of a chain, right? Oops, sorry. So this has 3 carbons, and then the rest is filled out by hydrogens, and you can see the boiling point goes up again. So the distinction between a hydrocarbon and a polymer is pretty subtle, because if we just keep adding carbons like this, we'll eventually get to the structure of polyethylene, like you saw here, right? And so the difference is very subtle, so I thought I would show you this. In the same thing, you'll see that the boiling point continues to go up and up and up, and so that means that it'll start to become a liquid and eventually a solid at room temperatures. However, most polymers are not just simply hydrogen and carbon like polyethylene. They often have other types of organic groups involved in these molecules. So if we have an OH, that's an alcohol or a hydroxyl group. And so that, essentially if you think about methane and then replace one of these hydroxyl groups, you have alcohols. And then you can also have other functional groups in the same case. So this is essentially an oxygen attached to the same thing. You have acetic acid, which is this carboxyl. You have formaldehyde, which is the oxygen group here, the double bond. And you can also have a phenol, which is a ring shaped, as you can see here, and you have aromatic groups. So there's a lot of other functional groups and organic groups that can contribute to a polymer and its formation.